So you look up at the night sky, right? Between all those distant stars, it looks like a whole lot of absolutely nothing. But what if I told you that the vacuum of space isn't actually empty at all? We are gonna dive headfirst into a seriously mind-bending quantum mystery. Can completely empty space physically change the very nature of light? For decades, physicists have been going back and forth on this. But thanks to some absolutely incredible new astronomical data, we might finally have our answer. To get to the bottom of this, we have got to look way beyond Earth toward one of the absolute most extreme objects in the entire universe, a magnetar. This dead ultramagnetic star is basically forcing physicists to tear up the rulebook on how light behaves in a vacuum. Because as it turns out, when light travels across a void subjected to some truly intense conditions, that nothingness might actually be doing something quite dramatic to the light. Meet Magnetar 1E1547.5408. Yeah, I know, it sounds like a license plate, but it's actually a hyper-dense dead star. We are talking about an object packing more mass than our entire sun into a sphere it could drive across in about 5 minutes. And it spins completely around every 2 seconds. But the real kicker, its magnetic field is trillions of times stronger than Earth's. When astronomers pointed their telescopes at this specific magnetar, they realized the X-rays shooting out of it were polarized at levels almost 3 times stronger than our current model said was possible. Now you might be wondering, why is that so shocking? Well, imagine a massive stadium. You have got a massive crowd of people waving flags from totally different corners. The X-rays from the magnetar are kinda like those flags. They're coming from different glowing regions on a curved, rapidly spinning surface, not from one tiny fixed spotlight. Light leaving different parts of that surface naturally points in different directions. So if you stand miles away from that stadium, those distinct flag movements should overlap, mix together, and basically cancel each other out into a chaotic blur. By the time those photons travel thousands of light years to hit our telescopes, they should just be a messy, disorganized blur. But they aren't. So why doesn't the light just cancel out? Since the star is rotating and blasting out light from multiple regions all at once, why in the world do we observe such a strong, perfectly organized net polarization? Something out there in the dark is perfectly preserving or even maybe enhancing the organization of that light as it travels. And this is where things get really cool. The answer to this totally modern mystery, it actually traces back to a 90-year-old prediction that's suddenly stepping squarely into the spotlight. Back in 1936, quantum pioneers Werner Heisenberg and Hans Euler predicted that under super extreme conditions, the vacuum of space isn't actually an inert void. Fast forward to the 2021 launch of NASA's IXPE observatory and a massive 140-hour observation campaign in 2025, and we finally have the tools to test this nearly century-old hypothesis. Which leads us to a massive mind-bending question. Could a magnetic field powerful enough actually alter the physical properties of completely empty space? See, classical physics tells us that a vacuum is just emptiness. It's a silent stage where things happen, but it's not a player in the game. But quantum physics? It says, hold on, the stage itself can bend, it can react, and it can even push back. Normally, we think of empty space as just an inert, featureless void, right? But introduce a massive magnetic field and suddenly that space starts acting almost like a physical crystal. And a crystal physically treats differently oriented light in different ways as it passes through. Now, under this theory, the insane magnetic field of the magnetar gives the literal empty space around it a preferred direction, physically altering the light traveling through it. Physicists actually have a name for this phenomenon. It's called vacuum birefringence. It comes straight out of quantum electrodynamics, or QED. Under QED, a vacuum isn't empty. It is a chaotic, simmering sea of virtual particles like electrons and positrons constantly popping in and out of existence. Add a giant magnet and suddenly all those microscopic ghosts line up, turning the vacuum into a giant optical filter that refracts and polarizes light. But hold on, Let's just pause for a second, because this is where our daily intuition just totally hits a wall. How can absolute nothingness have optical properties that physically alter the path of photons? The actual difference in how the vacuum treats differently oriented light is vanishingly tiny. The effect on a single photon is unbelievably small, but if you stretch that effect across a massive magnetic envelope that's thousands of light years wide, those microscopic twigs snowball into a massive, undeniable signal that we can actually detect. Now you can imagine trying to test this here on Earth is an absolute nightmare. The proposed experimental setups to try and measure vacuum birefringence in a lab are incredibly complex. It requires a magnetic field about 100 million times stronger than our best lab equipment can even master. But thankfully, nature loves to show off, and it provided us with the ultimate ready-made cosmic laboratory, the Magnetar. So in 2025, astronomers decided to finally look. Using NASA's IXPE observatory, they stared at this cosmic magnet for 140 hours straight, coordinating with radio telescopes. They weren't just checking out how bright it was, they were zeroing in on the precise orientation of the X-ray light from 1E1547. Because what actually happens when you point our most advanced polarimetry tech at the universe's strongest magnet? The results from that deep stare were just stunning. The data revealed these incredibly distinct, undeniable patterns. Changes in the X-ray energy perfectly correlated with changes in polarization. And even more critically, as the star rotated every 2 seconds, the polarization direction actively shifted in a totally predictable way. The light wasn't a jumbled mess at all, it was highly organized. Get this, they observed polarization levels hitting nearly 80%. Just let that sink in for a second, 80%. That is literally the highest value ever detected in an object like this. It is far too strong and way too organized to just be a coincidence or some baseline emission from a chaotic stellar surface. So without the vacuum itself acting as a filter, this level of organization is practically impossible. If light leaves different parts of the magnetar with different orientations, much of that information should just mix together and cancel out over thousands of light years. Vacuum birefringence is literally the perfect puzzle piece to explain how the light is being actively reshaped and perfectly aligned as it escapes the star's vicinity. And this is exactly what researcher Hua Din-thi over at Rice University pointed out. The computer simulations back this up entirely. When they modeled the extreme environment of this dead star, reproducing the exact X-ray polarization signatures we see in the data practically requires the presence of vacuum birefringence. If you don't include it in the model, the math just falls apart. The models demand its existence. But hey, as hyped as we are about these findings, we have got to keep our scientific hats on, right? We have to ask the tough question, is this definitive, undeniable proof of vacuum birefringence, or could there be an alternative explanation? Like, could the physical surface of the star itself or the weird geometric shape of its atmosphere somehow mimic this exact effect without the vacuum playing any role? Because right now, there is still a bit of a debate among researchers. It all comes down to a sneaky little problem astronomers call observational degeneracies. Basically, if you assume the star has one specific shape, you might explain the light one way. But if you assume a slightly different shape, you suddenly need vacuum birefringence to make sense of it. The assumptions we make at the starting line completely change the finish line when we are trying to nail down a definitive physical law. So while this is undeniably some of the strongest evidence we have literally ever had for a 90-year-old quantum prediction, what's it actually going to take to turn this into undisputed proof? We are going to need to observe a lot more magnetars, map out their different geometries, and see if the vacuum birefringence model is the absolute only mathematical framework that can universally explain all of them. Ultimately, as we wrap up this episode, we are left staring at a pretty breathtaking truth. By looking deeply into the magnetic envelope of a dead star, thousands of light years away, we are forced to confront something profound about our own reality. Empty space isn't empty. It's a dynamic, living, reactive fabric. If the void of space can act like a crystal, literally bending and shaping light through an invisible shimmering sea of virtual particles, you really have to wonder, could this bizarre quantum effect eventually rewrite everything we know about the fundamental nature of reality itself? Keep questioning the universe, guys.